Okay, now that we've looked at the early theories of matter and we know a little bit more about the scientists that led us to discover the atom and these ideas about how the atom is put together and what it looks like, now we're going to look at the atom in particular and some more scientists that led us to look at the atom and more the inner workings of it. Now that we know the atom exists, we're going to more clearly define it and look at the different parts that actually make it up. Because if you look back at our Dalton and Democritus, they were just thought that the atom was it, that is the smallest particle. Well, it's not, and we know that it's not. So we're going to look at the scientists that led us to this discovery. Okay, I want to start off by just talking about the atom and what it is. Well, the atom is the smallest particle of an element that retains the properties of that element. Now you might think that because atoms are so small, there'd be no way to actually see them. However, there is an instrument called the scanning tunneling microscope that allows us to see individual atoms and actually to move the atoms around to form different shapes and different patterns. You see a picture here of one of those microscopes. Now we're going to look at the first particle that was discovered when dealing with the atom. What scientists observed in the late 1800s was some relationship between matter and electric charge. So they were investigating how electricity might behave in the absence of matter, so pretty much without air. So what they did was they studied what we call a cathode ray. And they used a vacuum pump to pump all the air out of these glass tubes, and you see a picture here of a cathode ray, or actually a cathode ray tube. The metal electrodes on either end are called terminals. The negative terminal is a cathode, and the positive terminal is called an anode. And as you can see there, it's hooked up to a voltage source, or just a battery. And what happened was, one day in the lab, when Sir William Crookes was studying these cathode ray tubes, where they are passing electricity through nothing, and all they have there inside the tube is a screen, he noticed a flash of light, and the flash of light was produced by some form of radiation striking that screen, and it was a coating. Okay. What happened was then later he worked some more on it, and he noticed that these rays were traveling from the cathode to the anode, and so therefore these rays became known as cathode rays. Now, this accidental discovery of this cathode ray led to one of the most important technological and social developments of the 20th century, and that would be the television. Scientists continued their research using the cathode ray tubes and eventually found out that cathode rays were a stream of charged particles, and these particles were negatively charged. So let's take a look here at a little video clip explaining a little more about how televisions fit into these cathode rays. And also, then we'll look at how that fits into our atom.
But then how does it get to be a picture again? Well, let's go back to the 3D BB. Inside every TV set, there's a big tube. You call it a picture tube, but the correct name is cathode ray tube. It takes the waves from the transmitter and turns them back into electrons. In the back of this tube, there's an electron gun which shoots the electrons at the front of the tube. The front of the tube is coated with a special chemical which lights up when the electrons hit it. And this is what makes the picture.
I get it. The orthicon tube turns the picture into electrons, and the cathode ray tube turns the electrons back into the picture.
Precisely, my boy.
Now we have a scientist by the name of J.J. Thomson. He came along and began to do these different experiments on these cathode ray tubes. And he wanted to look at the ratio of this charge of this particle to its mass. He was unable to determine mass directly because the particle is just too small. All they knew was that it was a negative charge. And he looked at these magnetic and electric fields. He was very careful about it, and he finally did determine this charge to mass ratio. And when he compared the charge these particles have to their mass, he noticed that this ratio was way, way, way less than that of the hydrogen atom, which is the lightest atom that they knew of. So this was a big discovery because it meant then that there were particles smaller than the atom, because this charge to mass ratio was smaller than the smallest atom they knew of. So this meant then, or proved, that Dalton was wrong, that atoms are indivisible into smaller subatomic particles. This was a really revolutionary discovery at the time, because Dalton's atomic theory had become so widely accepted. But Thomson was actually correct. He did identify the first subatomic particle, the electron. We then had another man that came along, and I'm just going to mention him. His name was Robert Millikan. He was in the late 1800s, and he finally then actually determined the charge of the electron so that he could figure out the mass. And the mass of an electron is very, very, very small. This raised then some new questions with this discovery of the electron. If electrons are part of all matter and they possess a negative charge, how is it that all matter is neutral? So we're missing some charges there. And they were also wondering at the time, if the mass of an electron is so small, then what accounts for the rest of the mass in a typical atom? Because the electron was really, really tiny, but we know that all these atoms have mass, so what's making up the rest of this mass? And that's where we're going to get into another scientist. Alright, we're going to look actually again at J.J. Thomson before we move on to another scientist. He tried to answer those questions that I just proposed, and he came up with what was called the plum pudding model. And what he said was that there was a spherically shaped atom composed of a uniformly distributed positive charge. And then we had all these negative electrons that were kind of scattered throughout the entire atom. And it looks kind of like a chocolate chip cookie dough or plum pudding at the time, as you can tell here by the picture. And all those electrons that are just scattered throughout. And this model really did not last very long at all. It was just the first one to come along. Well, that leads us to actually the better model here that Ernest Rutherford came up with. There was a small group of scientists and Ernest Rutherford, and he designed and conducted an experiment to see if alpha particles would be deflected as they passed through a thin foil of gold. Alpha particles are just big particles. Okay, they're actually helium atoms. So he was shooting these big particles at a very, very thin piece of gold foil. What happened when these alpha particles struck the gold foil, you'd see a flash of light produced on this coated screen surrounding the foil. And as you can see in the picture here, you have the circular screen, and then the gold foil in the middle, and then that block on the other end is just the alpha particle emitting source. So it's the thing that's shooting out the alpha particles. And what happened was they noted where these flashes occurred. The scientists could determine if the atoms in the gold foil deflected the alpha particles or if the alpha particles just passed straight through to the other side. They would see these gold flashes on the other side if they passed right through, and if they got deflected off the gold foil, they would see the gold flashes more in front of the gold foil. So we're going to look at a couple of different short little video clips here that are going to kind of explain his experiment a little bit better, and then I'm going to go back and talk about it a little more as well.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So what you saw in both of those little video clips, and then what Rutherford saw, so you saw what Rutherford and his fellow scientists discovered after doing this test. And they were amazed that a few of the alpha particles were deflected at these very large angles. And we have these two pictures here at the bottom. So what he discovered then was that the plum pudding model could not be right because an electron would not deflect a very large alpha particle. It's like if I had a bowling ball and I was throwing it at a tennis ball, and the tennis ball bounced the bowling ball straight back at me. That's not going to happen. The tennis balls are tiny. So he decided then that there has to be some center, some very massive center to these gold foil atoms. And he came up with this model that there was tons of empty space through which electrons moved, because they did have a lot of the particles that passed straight through. So that means they didn't touch anything. But then it also had to have a very tiny, dense region that he called the nucleus. And he decided that this region was centrally located and contained all of the atom's positive charge and pretty much all of the mass. So that was the mass problem they were having, as to how do we account for all this mass in an atom if I just have a little electron? Well, I also have a very dense positive center that has lots and lots of mass. So according to Rutherford's new model, most of the atom was electrons moving through empty space, and the electrons were held in space by their attraction to the positively charged nucleus. Keep in mind, okay, if an atom had the diameter of 2 football fields, the nucleus would be the size of a nickel. But it would also have the mass of probably thousands of automobiles. Very small, very dense. Finally, we're going to complete the atom and look at the discovery of our final 2 particles. Rutherford then refined the nucleus and discovered the positively charged proton. Protons are a subatomic particle that carry an equal but opposite charge of the electron. They are positive. It took a little while later, but a co-worker of Rutherford by the name of James Chadwick showed that the nucleus also contained another subatomic particle, a neutral one that he called the neutron. The neutron is pretty much the same mass as a proton, but does not have a charge. Since atoms are neutral, the number of protons in the nucleus will equal the number of electrons surrounding the nucleus.